This presentation is delivered by the Stanford Center for Professional Development.
So, what I want to do today is talk about a different type of learning algorithm, and in particular start to talk about generative learning algorithms and a specific algorithm called Gaussian discriminant analysis. Take a slight digression to talk about Gaussians, and I'll briefly discuss generative versus discriminative learning algorithms, and then hopefully wrap up today's lecture with a discussion of naive Bayes and Laplace smoothing. So just to motivate our discussion on generative learning algorithms, right? So by way of contrast, the sorts of classification algorithms we're talking about, I think of as algorithms that do this. So you're given a training set, and if you run an algorithm like logistic regression on this training set, the way I think of logistic regression is that it's trying to look at the data and it's trying to find a straight line to divide the crosses and the O's, right? So trying to find a straight line, let's make the data set a bit noisier. Trying to find a straight line that separates out the positive and the negative crosses as well as possible. Right. In fact, it shows something on the laptop. Maybe we can just use the screens on the small monitors for this. In fact, you can see, there's a data set with logistic regression. And so I've initialized the parameters randomly. And so logistic regression is currently outputting the current hypothesis that iteration 0 is that straight line shown on the bottom right. And so after one iteration of gradient descent, the straight line changes a bit. After 2 iterations, 3, 4, until logistic regression converges and is found a straight line that more or less separates the positive and negative class. Okay, so you think of this as logistic regression sort of searching for a line that separates the positive and the negative classes. What I want to do today is talk about an algorithm that does something slightly different. And to motivate this, let's use our old example of trying to classify between malignant cancer and benign cancer. Right? So a patient comes in and they have a cancer. You want to know if it's a malignant or a harmful cancer, or if it's a benign, meaning a harmless cancer. So rather than trying to find a straight line to separate the two classes, here's something else we could do. We can go through our training set and look at all the cases of malignant cancers, go through, look for our training set for all the positive examples of malignant cancers, and we can then build a model for what malignant cancer looks like. Then we'll go for a training set again and take out all the examples of benign cancers, and then we'll build a model for what benign cancers look like. Okay? And then when you need to classify a new example, when you have a new patient and you want to decide is this cancer, malignant or benign, you then take your new cancer and you match it to your model of malignant cancers, and you match it to your model of benign cancers, and you see which model it matches better. And depending on which model it matches better to, you call that, you then predict whether the new cancer is malignant or benign. Okay? So what I just described, this class of methods where you build a separate model for malignant cancers and a separate model for benign cancers is called a generative learning algorithm. And let me just go ahead and formalize this. So in the models that we've been talking about previously, those were actually all discriminative learning algorithms. And slightly more formally, a discriminative learning algorithm is one that either learns P of y given x directly, or even learns a hypothesis that outputs values 0, 1 directly. Okay, so logistic regression is an example of a generative learning algorithm. Is an example of a discriminative learning algorithm. In contrast, a generative learning algorithm models P of x given y the probability of the features given the class label. And as a technical detail, it also models P of y, but that's a less important thing. And the interpretation of this is that a generative model builds a probabilistic model for what the features looks like, conditioned on the class label. Okay? In other words, conditioned on whether a cancer is malignant or benign, it models probability distribution over what the features of the cancer looks like. Then having built this model, having built a model for P of x given y and P of y, then by Bayes' rule, obviously you can compute P of y given 1 conditioned on x. This is just P of x given y equals 1 times P of x divided by P of x. And if necessary, you can calculate the denominator using this, right? Right? And so by modeling P of x given y and modeling P of y, you can actually use Bayes' rule to get back to P of y given x. But a generative learning algorithm starts modeling P of x given y rather than P of y given x. Okay? We'll talk about some of the trade-offs and why this may be a better or worse idea than a discriminative model a bit later. Let's go for a specific example of a generative learning algorithm. And for this specific motivating example, I'm going to assume that your input features x are in Rn and are continuous valued. Okay? And under this assumption, let me describe to you a specific algorithm called Gaussian discriminant analysis. And the, I guess, core assumption is that we're going to assume in the Gaussian discriminant analysis model that P of x given y is Gaussian. Okay? So, actually, just raise your hand. How many of you have seen a multivariate Gaussian before? Not a 1D Gaussian, but a high dimensional. Okay, cool. Like maybe half of you, 2/3 of you. So let me just say a few words about Gaussians, and for those of you that have seen it before, it'll be a refresher. So we say that a random variable z is distributed Gaussian, multivariate Gaussian, as script n for normal, with parameters mean, mu, and covariance sigma squared. If z has a density 1/2 pi, 1/2. Okay, that's the formula for the density. It's a generalization of the one-dimensional Gaussian, the normal, the familiar bell-shaped curve, to higher dimension vector value random variable z. Don't worry too much about this formula for the density. I don't know, you rarely end up needing to use it. But the two key quantities are this vector mu is the mean of the Gaussian, and this matrix sigma is the covariance matrix. Covariance. And so, sigma would be equal to, right, the definition of covariance of a vector value random variable is, x minus mu transpose. Okay? And actually, if this doesn't look familiar to you, you might rewatch the discussion section that the TAs held last Friday, or the one that they'll be holding later this week on sort of a recap of probability. Okay, so multivariate Gaussian is parameterized by a mean and a covariance. And let me just, can I have the laptop display, please? Let me just go ahead and actually show you, graphically the effect of varying a Gaussian, varying the parameters of a Gaussian. So what I have up here is a zero mean is the density of a zero mean Gaussian with covariance matrix equals the identity. The covariance matrix is shown in the upper right-hand corner of the slide. And this is a familiar bell-shaped curve in 2 dimensions. And so if I shrink the covariance matrix, instead of covariance or identity, if I shrink the covariance matrix, then the Gaussian becomes more peaked. And if I widen the covariance, so like sigma equals 2, then the distribution or the density becomes more spread out. Okay. There's back to standard normal, identity covariance 1. If I increase the diagonals of the covariance matrix, right? If I make the variables correlated, then the Gaussian becomes flattened out in this x equals y direction. If I increase it even further, then my variables x and y, right, on the excuse me, x, because z1 and z2, or my 2 variables on the horizontal axis become even more correlated. To show the same thing in contours, the standard normal distribution has contours that they're actually circles. Because of the aspect ratio, these look like ellipses. These should actually be circles. And if you increase the off diagonals of the Gaussian covariance matrix, then it becomes ellipses aligned along the 45-degree angle in this example. And the same thing, here's an example of a Gaussian density with negative covariances. So now the correlation goes the other way, so even stronger negative covariance, and the same thing in contours. So the Gaussian with negative entries on the diagonals and even larger entries on the diagonals. Okay, so and the other parameter for the Gaussian is the mean parameter. So this is with mean 0, and as you change the mean parameter, this mu equals 0, 1.5, the location of the Gaussian just moves around. Okay. All right, so that was a quick primer on what Gaussians look like. And here's, as a roadmap, or as a picture to keep in mind when we describe the Gaussian discriminant analysis algorithm, this is what we're going to do. Here's the training set. And in the Gaussian discriminant analysis algorithm, what I'm going to do is I'm going to look at the positive examples, say the crosses, and just looking at only the positive examples, I'm going to fit a Gaussian distribution to the positive examples. And so maybe I end up with a Gaussian distribution like that. Okay, so that's P of x given y equals 1. And then I'll look at the negative examples, the O's in this figure, and I'll fit a Gaussian to that. And maybe I get a Gaussian centered over there. This is the contours of my second Gaussian. And together, and we'll say how later, together these 2 Gaussian densities will define a separator for these 2 classes. Okay, and it'll turn out that the separator will turn out to be a little bit different from what logistic regression gives you. If you run logistic regression, you actually get the decision boundary shown in the green line, whereas Gaussian discriminant analysis gives you the blue line. Okay, switch back to chalkboard, please. All right. Here's the Gaussian discriminant analysis model. Going to model P of y as a Bernoulli random variable as usual, but as a Bernoulli random variable and parameterized by parameter phi. So you've seen this before. Model P of x, excuse me, given y equals 0 as a Gaussian. Oh, you know what? Yes, excuse me. I thought this looked strange. There should be a sigma, determinant of sigma to the 1/2 in the denominator there. It's no big deal. It's, yeah, well. Okay. Right, I was missing the sigma to the determinant of sigma to the 1/2 on the previous board, excuse me. Okay, and so I model P of x given y equals 0 as a Gaussian with mean mu 0 and covariance sigma, so the sigma to the minus 1/2. And And so the parameters of this model are phi, mu 0, mu 1, and sigma. And so I can now write down the likelihood of the parameters as, actually the log likelihood of the parameters as the log of that. Right? So in other words, if I'm given a training set, then I can write down the log likelihood of the parameters as the log of, the product of probabilities of p of xi comma yi. Right? And this is just equal to that, where each of these terms, p of xi given yi or p of yi, is then given by one of these three equations on top. Okay? And I just want to contrast this again with discriminative learning algorithms, right? So this, to give this a name, I guess, this sometimes is actually called the joint data likelihood, the joint likelihood. And let me just contrast this with what we had previously when we were talking about logistic regression, where I said that the log likelihood of the parameters theta was log of a product I equals 1 to m, p of yi given xi and parameterized by theta, right? So back when we're fitting logistic regression models or generalized linear models, we're always modeling p of yi given xi and parameterized by theta. And this was the conditional likelihood, right? In which we're modeling p of yi given xi. Whereas now, with generative learning algorithms, we're going to look at the joint likelihood, which is p of xi comma yi. Okay? So, let's see. So, given training sets and using the Gaussian discriminant analysis model, to fit the parameters of the model, we'll do maximum likelihood estimation as usual. And so you maximize L with respect to the parameters phi, mu 0, mu 1, sigma. And so when we find the maximum likelihood estimate of the parameters, you find that phi is the maximum likelihood estimate is actually no surprise. I'm writing this down mainly as a practice for indicator notation. Right? So the maximum likelihood estimate for phi will be sum over I yi divided by m. Or written alternatively as sum over all your training examples of indicator yi equals 1 divided by m. Okay? In other words, maximum likelihood estimate for the Bernoulli parameter phi is just the fraction of training examples with label 1, with y equals 1. Maximum likelihood estimate for mu 0 is this. Okay? You should stare at this for a second and see if it makes sense. Actually, I've just write out the next one for mu 1. You do that. Okay. So what this is well, the denominator is sum of your training set indicator yi equals 0. So for every training example for which yi equals 0, this will increment the count by 1. Right? So the denominator is just the number of examples with label 0. Right? And then the numerator will be, let's see, sum from I equals 1 through m. Well, every time yi is equal to 0, this will be 1, and otherwise this thing will be 0. And so, this indicator function means that you're including only the terms for which yi is equal to 1, only the terms for which y is equal to 0. Because for all the terms where yi is equal to 1, this summand would be equal to 0. And then you multiply that by xi, and so the numerator is the sum of xi's corresponding to examples where the clause labels were 0. Okay? Raise your hand if this makes sense. Yeah. Okay, cool. So just to say this less fancifully, this just means look for your training set, find all the examples for which y equals 0, and take the average of the value of x for all your examples for which y equals 0. So take all your negative training examples and average the values for x, and that's mu 0. Okay? If this notation is still a little bit cryptic, if you're still not sure why this equation translates in what I just said, so do go home and stare at it for a while until this makes sense. And this sort of no surprise. It just says estimate the mean for the negative examples, take all your negative examples and average them. It's sort of no surprise, but this is a useful practice of indicator notation. Again, you can derive the maximum likelihood estimate for sigma. I won't do that. You can read that in the notes yourself. And so, having fit the parameters, phi, mu 0, mu 1, and sigma to your data, we now need to make a prediction. Now, when you're given a new value of x, when you're given a new cancer, you need to predict if it's malignant or benign. Your prediction is then going to be, let's say, the most likely value of y given x. I should write semicolon the parameters there, but I'll just skip that. Which is the argmax over y by Bayes' rule. Right? And that is in turn just that, because the denominator p of x doesn't depend on y. And if p of y is uniform, in other words, if each of your clauses is equally likely, so p of y takes the same value for all values of y, then this is just argmax over y, p of x given y. Okay. This happens sometimes, maybe not very often. So usually you end up using this formula where you compute p of x given y and p of y using your model. Okay. Oh, let's see. So so if you take, actually, let me. So the min of argmax means the value for y that maximizes this, right? So just a current example, the min of x minus 5 squared is 0 because by choosing x equals 5, you can get this to be 0, and the argmin over x of x minus 5 squared is equal to 5 because 5 is the value of x that makes this minimize. Okay. Cool. Okay. Thanks for asking that. Okay. Actually, any other questions about this? Yeah.
Y is distributed Bernoulli. Why is it a uniform? The probability of Y is Bernoulli,
but I see. By uniform, I meant I was being loose here. I meant if p of y equals 0 is equal to p of y equals 1, or if y is the uniform distribution over the set 0 and 1. Yeah, right. I just meant, yeah, if P of y equals 0 equals P of y given 1. That's all I meant. See? Yeah. Anything else? Okay, so turns out Gaussian discriminant analysis has an interesting relationship to logistic regression. Let me illustrate that. So let's say you have a training set. Actually, let me just go and draw a 1D training set, and that'll kind of work, yes. Okay. So let's have a training set comprising a few negative and a few positive examples. And let's say I run Gaussian discriminant analysis, so I'll fit Gaussians to each of these two densities, fit a Gaussian density to each of these two, to my positive and my negative training examples. And so maybe my positive examples, the x's are fit with a Gaussian like this. And my negative examples, I will fit maybe with a Gaussian that looks like that. Okay? Now, hope this picture makes sense, right? Now, let's vary along the x-axis. And what I want to do is I'll overlay on top of this plot. So I'm going to plot P of y equals 1. Actually, given x for a variety of values x. Okay? So I actually realized what I should have done. I'm going to call the x's the negative examples. I'm going to call the o's the positive examples. Okay? This makes this plot come nicer. So let's take a value of x is fairly small. Let's say x is this value here on the horizontal axis. Then what's the probability of y being equal to 1 conditioned on x? Well, the way you calculate that is, right, P of y equals 1 given x. I mean, you plug in all of these formulas as usual, right? It's P of x given y equals 1, which is your Gaussian density, times P of y equals 1, which is essentially this is just going to be equal to phi, and then divided by, right, P of x. And I showed you how you can calculate this. But using these two Gaussians and my product on P of y, actually compute what P of y equals 1 given x is. And in this case, if x is this small, clearly it belongs to the left Gaussian. It's very unlikely to belong to a positive clause. And so it'll be very small. It'll be very close to 0, say. Okay? And then we can increment the value of x a bit and consider a slightly different value of x. And plot what is the P of y given x. P of y equals 1 given x. And again, it'll be pretty small. Let's choose a point like that, right? At this point, the two Gaussian densities have equal value. And if I ask, if x is this value, right, shown by the arrow, what's the probability of y being equal to 1 for that value of x? Well, you really can't tell. So maybe it's about 0.5. Okay? And if you fill in a bunch more points, get a curve like that. And then you can keep going. Let's say for a point like that, you can ask, what's the probability of x being 1? Well, if it's that far out, then clearly it belongs to this rightmost Gaussian. And so the probability of y being 1 would be very high. It would be almost 1. Okay? And so you can repeat this exercise for a bunch of points. Right? Compute P of y equals 1 given x for a bunch of points. And if you connect up these points, you find that the curve you've just plotted takes the form of a sigmoid function. Okay? So in other words, when you make the assumptions under the Gaussian discriminative Gaussian discriminant analysis model that P of x given y is Gaussian, when you go back and compute what P of y given x is, you actually get back exactly the same sigmoid function that we're using in logistic regression. Okay? But it turns out the key difference is that Gaussian discriminant analysis will end up choosing a different position and a steepness of the sigmoid than with logistic regression. What's the question?
I was just wondering, the Gaussians are field wide. I don't know if you do.
No. Let's see. The Gaussian. So this Gaussian is p of x given y equals 0, given y equals 1, and this Gaussian is p of x given y equals 0. Does that make sense? Okay. Anything else? Yeah.
How did you, when you were drawing all the dots, how did you decide what y and p of x was?
What? Say that again?
Oh, I guess I'm sorry. Could you go over how you figured out where to draw each dot?
Let's see. Okay, so so the computation is as follows, right? The steps are, I have a training set, and so given my training set, I'm going to fit a Gaussian discriminant analysis model to it. And what that means is, I'll build a model for p of x given y equals 1. I'll build a model for p of x given y equals 0. And I'll also fit a Bernoulli distribution to p of y. Okay, so in other words, given my training set, I'll fit p of x given y and p of y to my data. And now I've chosen my parameters phi, mu 0, mu 1, and sigma. Okay? Then this is the process I went through to plot all these dots, right? It's just I pick a point on the x-axis, and then I compute p of y given x for that value of x. And p of y given 1 conditional on x will be some value between 0 and 1. It will be some real number. And whatever that real number is, I then plot it on the vertical axis. Okay? And the way I compute p of y equals 1 conditioned on x is I would use these quantities. I would use p of x given y and p of y and sort of plug it into Bayes' rule. And that allows me to compute p of y given x from, these three quantities. Does that make sense? Yeah. Was there something more that...
And how did you model p of x? Is that...
Oh, okay. Yeah, so, well, this earlier. So p of x can be written as, right, so p of x given y equals 0 times p of y equals 0 plus p of x given y equals 1, p of y equals 1. Right. So, and so each of these terms, p of x given y and p of y, these are terms I can get out of directly from a Gaussian discriminant analysis model. These are right, each of these terms is something that my model gives me directly. So I'll plug that into the denominator. And by doing that, that's how I compute p of y equals 1 given x. Make sense? Okay. Cool. So, so let's talk a little bit about the advantages and disadvantages of using a generative learning algorithm. Right? So in the particular case of Gaussian discriminant analysis, we assume that x conditioned on y is Gaussian. Right. And the argument I showed on the previous chalkboard, I didn't prove it formally, but you actually go back and prove it yourself, is that if you assume x given y is Gaussian, then that implies that when you plot y given x, you find that, well, let me just write logistic posterior. Okay? And the argument I showed just now, which I didn't prove, you can go ahead and prove it yourself, is that if you assume x given y is Gaussian, then that implies that the posterior distribution, or the form of p of y given x, given the form of p of y equals 1 given x, is going to be a logistic function. And it turns out this implication in the opposite direction does not hold true. Okay. In particular, it actually turns out, this is actually kind of cool. It turns out if you assume that x given y equals 1, so it is Poisson with parameter lambda 1, and x given y equals 0 is Poisson with parameter lambda 0. It turns out if you assume this, then that also implies that P of y given x is logistic. Okay? So there are lots of assumptions on x given y that would lead to P of y given x being logistic. And therefore, the assumption that x given y being Gaussian is a stronger assumption than the assumption that y given x is logistic. Okay? Because this implies this, right? That means that this is a stronger assumption than this. Because the logistic posterior holds whenever x given y is Gaussian, but not vice versa. And so this leads to one of the trade-offs between Gaussian discriminant analysis and logistic regression. Right? Gaussian discriminant analysis makes a much stronger assumption that x given y is Gaussian. And so when this assumption is true, or when this assumption approximately holds, if you plot the data, and if x given y is indeed approximately Gaussian, then if you make this assumption explicit in the algorithm, then the algorithm will do better. Because it's as if the algorithm is making use of more information about the data. The algorithm knows that the data is Gaussian. Right? And so if the Gaussian assumption, holds or roughly holds, then Gaussian discriminant analysis may do better than logistic regression. If conversely, if you're actually not sure what x given y is, then logistic regression, the discriminative algorithm, may do better. And in particular, if you use logistic regression, and maybe you secretly thought the data was Gaussian, but it turned out the data was actually Poisson, right? Then logistic regression will still do perfectly fine. Because if the data were actually Poisson, then P of y equals 1 given x will be logistic, and it'll do perfectly fine. But if you assumed it was Gaussian, then the algorithm may go off and do something that's not as good. Okay? So it turns out that, right. So to say it slightly differently, it turns out that the real advantage of generative learning algorithms is often that it requires less data. And in particular, data is never really exactly Gaussian, right? This data is often approximately Gaussian, it's never exactly Gaussian. And it turns out generative learning algorithms often do surprisingly well, even when these modeling assumptions are not met. But one other trade-off is that by making stronger assumptions about the data, Gaussian discriminant analysis often needs less data in order to fit like an OK model, if you have less, even if you have less training data. Whereas in contrast, logistic regression, by making less assumptions, is more robust to your modeling assumptions because you're making a weaker assumption, making less assumptions. But sometimes it takes a slightly larger training set to fit than Gaussian discriminant analysis. This question?
Here, do we need any assumption about the number of samples? Because here we assume that P of y equals 1 is equal to number of positive samples over whole number of samples. It's true when the number of samples is large enough.
Okay, so let's see. So there's this question was sort of, is this true? What was that? So let me try to answer that differently. So the modeling assumptions are made independently of the size of the training set, right? Yeah, so, like in least squares regression, well, in all of these models, I'm assuming that these are random variables drawn from some distribution, and then finally I'm giving a single training set, and then I estimate the parameters of the distribution, right? So
what's the probability of y equals 1?
Probably of y equals 1?
Yeah, we use
Okay,
that.
So this raises, getting a little bit back to the philosophy of maximum likely estimation, right? I'm assuming that their P of y is equal to phi to the y, 1 minus phi to the y. 1 minus y. So I'm assuming that there's some true value of y generating all my data. And then, well, when I write this, I guess, maybe what I should write isn't. So when I write this, I guess there are really two values of phi. One is there's a true underlying value of phi that, you know, God used to generate the data. And then there's the maximum likelihood estimate of the value of phi. And so when I was writing those formulas earlier, those formulas are writing for phi and mu0 and mu1 were really the maximum likelihood estimates for phi, mu0, and mu1. And that's different from the true underlying values of phi, mu0, and mu1. But yeah, right. So the maximum likelihood estimate comes from the data. And there's some sort of true underlying value of phi that I'm trying to estimate. And my maximum likelihood estimate is my attempt to estimate the true value. But, you know, by notational convention, often I'll just write this as that as well, without bothering to distinguish between the maximum likelihood value and the true underlying value that I'm assuming is out there, and that I'm only hoping to estimate. Actually, yeah, but if so philosophical questions like these about maximum likelihood and so on, I hope the TAs, the Friday discussion sections, is a good time to ask questions about sort of probabilistic definitions like these as well. Are there other questions? No. Yeah. Right. Okay. So. Right. Oh, turns out, let me just mention one more thing that's kind of cool. I said that if x given y is Poisson, then you also get a logistic posterior. It actually turns out there's a more general version of this. If you assume x given y equals 1 is exponential family with parameter a to 1, and if you assume x given y equals 0 is exponential family with parameter a to 0, then this implies that p of y equals 1 given x is also logistic. Okay, and that's kind of cool. So it means that, you know, y given x could be, I don't know, some strange thing. It could be gamma, because we've seen Gaussian. Y given x could be, I don't know, gamma exponential, Dirichlet beta. I'm just rattling off my mental list of exponential family distributions. It could be any one of those things. So long as the same exponential family distribution for the two clauses with different natural parameters, then the posterior p of y given 1 given x, p of y equals 1 given x will be logistic. And so this shows the robustness of logistic regression to the choice of modeling assumptions, because it could be that the data was actually, you know, gamma distributed, and this still turns out to be logistic. So it's the robustness of logistic regression to modeling assumptions. And yeah, right. And this incidentally, I think early on I promised two justifications for where I pulled the logistic function out of the hat, right? So one was the exponential family derivation we went through last time, and this is sort of the second one, that all of these modeling assumptions also lead to the logistic function. Yeah.
Is the final substitute? If it's the posterior is logistic, that
that y equals 1 given is logistic, then this implies that? No, this is also not true, right? So, yeah, so this exponential family distribution implies y equals 1 is logistic, but the reverse assumption is also not true. There are actually all sorts of really bizarre distributions for x that would give rise to the logistic function. Okay, so let's talk about, those are first generative learning algorithm. Let me now talk about the second generative learning algorithm. And the motivating example, actually this is called the naive Bayes algorithm. And the motivating example that I'm going to use would be spam classification. Right? So let's say that you want to build a spam classifier, you know, to take your incoming stream of email and decide if it's spam or not. So let's see. Y will be 0 or 1, with 1 being spam email and 0 being non-spam. And the first decision we need to make is, given a piece of email, how do you represent a piece of email using a feature vector x? Right? So email is just a piece of text, right? You get your email is like a list of words, or a list of ASCII characters. So how do you represent email as a feature vector x? So we'll use a couple of different representations, but the one I'll use today is we will construct the vector x as follows. I'm going to go through my dictionary and to make a listing of all the words in my dictionary. Okay, so the first word is RA. The second word in my dictionary is aardvark. R is wolf. Okay. You know, maybe somewhere along the way you see the word buy. In the spam emails, and you buy stuff. Depending on how you collect your list of words, you know, you won't find CS229, right, close number in a dictionary, but if you collect a list of words via your other emails you've gotten, you have this list somewhere as well. And then the last word in my dictionary was zigmergy, which pertains to technological chemistry that deals with the fermentation process in brewing. So I get a piece of email, and what I'll do is I'll then scan through this list of words, and wherever a certain word appears in my email, I'll put a 1 there. So if I get a piece of email and it has the word A, then that's 1. You know, my email doesn't have words aardwolf or aardvark, so I get zeros. I get a piece of email and they want me to buy something, CS229 doesn't appear, and so on. Okay? So this would be one way of creating a feature vector to represent my a piece of email. Now, let's build a generative model out for this. Actually, let's use this. In other words, I want to model P of x given y equals 0, y equals 1, right? And my feature vectors are going to be 0, 1 to the n. It's going to be these bit vectors, binary value vectors, they're n-dimensional, where n may be, you know, on the order of, say, 50,000, if you have 50,000 words in your dictionary, which is not atypical. So values from, I don't know, mid-thousands to tens of thousands is fairly typical for problems like these. And therefore, there are 2 to the 50,000 possible values for x, right there. So 2 to the 50,000 possible bit vectors of length 50,000. And so, you know, one way to model this is a multinomial distribution. But because there are 2 to the 50,000 possible values for x, I would need, you know, 2 to the 50,000, like maybe -1 parameters, right? Because they have to sum to 1, right? So -1. And this is clearly way too many parameters to model using a multinomial distribution over all 2 to 50,000 possibilities. So, in the naive Bayes algorithm, I'm going to make a very strong assumption on P of x given y. In particular, I'm going to assume, let me just say what it's called, then I'll write out what it means. I'm going to assume that the xi's are conditionally independent. Given y. Okay, let me say what this means. So I have that P of x1, x2, up to x 50,000, right, given y. By the chain rule of probability, this is P of x1 given y times P of x2 given y comma x1 times P of, well, let me just put ... Oh, let's write one more. Times ... up to, you know, well, whatever. You get the idea, up to P of x 50,000. Okay? So this is the chain rule of probability. This always holds. I've not made any assumption yet. And now, I'm going to make what's called the naive Bayes assumption, or this assumption that the xi's are conditionally independent given y. I'm going to assume that, well, nothing changes for the first term. But I'm going to assume that p of x2 given y comma x1 is equal to p of x2 given y. I'm going to assume that that term is equal to p of x3 given y, and so on, up to p of x 50,000 given y. Okay? Or just written more compactly, I'm going to assume that p of x1 through x 50,000 given y is the product from I equals 1 to 50,000 of p of xi given y. Okay? And stated informally, what this means is that I'm sort of assuming that so long as you know the class label y, so long as you know whether this is spam or not spam, then knowing whether the word A appears in email does not affect the probability of whether the word oddwolf appears in email. All right? And in other words, we're assuming that once you know whether email is spam or not spam, then knowing whether other words appear in email won't help you predict whether any other word appears in email. Okay? And obviously, this assumption is false, right? This assumption can't possibly be true. I mean, if you see the word, I don't know, CS229 in an email, you're much more likely to see my name in the email or the TA's names or whatever. So this assumption is normally just false under English, right? For normal written English. But it turns out that despite this assumption being sort of false in the literal sense, the naive Bayes algorithm is sort of an extremely effective algorithm for classifying text documents into spam or not spam, or for classifying your emails into different email folders for you automatically, or for looking at web pages and classifying whether this web page is trying to sell something or whatever. It turns out this assumption works very well for classifying text documents, and for other applications too that I'll talk a bit about later. As a digression that that makes sense only to some of you, let me just say that if you're familiar with Bayesian networks and graphical models, the Bayesian network associated with this model looks like this. And you're assuming that there's a random variable y that then generates x1, x2 through x 50,000. Okay? If you've not seen a Bayes net before, if you don't know a graphical model, just ignore this. It's not important to our purposes. But if you've seen it before, that's what it will look like. Okay. So, the parameters of the model are as follows. With phi of I given y equals 1, which is probably if x equals 1, xi equals 1 given y equals 1, phi I given y equals 0, and phi y. Okay, so these are the parameters of the model, and therefore, to fit the parameters of the model, you can write down the joint likelihood, right? Is equal to, as usual, so given a training set, you can write down the joint likelihood of the parameters and then when you do maximum likelihood estimation, you find that the maximum likelihood estimate of the parameters they're really pretty much what you'd expect. Maximum likelihood estimate for phi j given y equals 1 is sum from I equals 1 to m indicator xij equals 1, comma, yi equals 1. Okay. And this is just I guess, stated more simply, the numerator just says, run through your entire training set, sum for all training examples, and count up the number of times you saw word J in a piece of email for which the label Y was equal to 1. So in other words, look for all your spam emails and count the number of emails in which the word J appeared out of all your spam emails. And the denominator is, sum from I equals 1 to m, the number of spam, the denominator is just the number of spam emails you got. And so this ratio is, in all your spam emails in your training set, what fraction of these emails did the word J appear in? Did the J word in your dictionary appear in? And that's the maximum likelihood estimation that's the maximum likelihood estimate for the probability of seeing word J conditioned on a piece of email being spam. Okay. Similarly, your maximum likelihood estimate for phi y is pretty much what you'd expect, right? Okay. And so, having estimated all these parameters, when you're given a new piece of email that you want to classify, you can then compute P of y given x using Bayes' rule, right? Same as before, because together these parameters gives you a model for P of x given y and for P of y. And by using Bayes' rule, given these two terms, you can compute P of x given y. And there's the spam classifier. Okay. Turns out we need one more elaboration to this idea, but let me check if there are questions about this so far.
Does this model depends on the number of inputs?
What do you mean number of inputs? Number of features?
No, number of samples.
Yeah, I mean, well, m is the number of training examples. So this, given m training examples, this is the formula for the maximum likelihood estimate of the parameters. Right, so. Other questions? Does it make sense? Right, m is the number of training examples. So when you have m training examples, you plug it into this formula, and that's how you compute the maximum likelihood estimates.
Does it mean m is the number of emails?
Yeah, right. So to collect a training set, I would go through, all the email I've gotten in the last 2 months, and label them as spam or not spam. And so you'd have, I don't know, like a few hundred emails or a few hundred emails labeled as spam or not spam, and that will comprise your training set, right? X1, Y1 through XM, YM, where X is one of those vectors representing which words appeared in the email, and Y is 0, 1, depending on whether I label spam or not spam. Okay?
So you're saying that this model depends on the number of samples, but the last model doesn't depend on the number of samples. But here phi is the same for me. Right?
So the different things, right? There's a model which is the modeling assumptions I've made, right? I'm assuming that I'm making the naive Bayes assumption. So the probabilistic model is an assumption on the joint distribution of x and y. That's what the model is. And then I'm given a fixed number of training examples. I'm given m training examples, and then sort of after I'm given a training set, I'll then go and derive the maximum likely estimate of the parameters, right? So that's sort of maybe we should take that offline. If yeah, last question.
Then how did you select the 50,000 words though?
Say that again.
How did you select the 50,000 words?
Oh, okay. How does select the 50,000 words? Yeah. So it turns out this is a sort of very practical question, right? How do I count this list of words? One common way to do this is to actually find some way to come up with a list of words. Like go through all your emails, go through all the. In practice, one common way to come up with this list of words is to just take all the words that appear in your training set. That's one fairly common way to do it. Or you could, or if that turns out to be too many words, you can take all words that appear at least 3 times in your training set. You know, so words that you didn't even see 3 times in the emails you got in the last 2 months, you discard. So those are. I was talking about going through a dictionary, which is a nice way of thinking about it. But in practice, you might go through, you know, your training set and just take the union of all the words that appear in it. And sometimes there's sort of even better ways to select these features. But this is one way to think about creating your feature vector, right, as 0 and 1 values. Okay. And then, yeah. Okay. Last question.
I'm not entirely clear how you came up with the parameters.
How I came up with the parameters? Okay, so let's see. So in naive Bayes, what I need to do, the question is how do I come up with the parameters, right? So in naive Bayes, I need to build a model for P of x given y and for P of y, right? So this is I mean, in generative learning algorithms, I need to come up with models for these. So how do I model P of y? Well, I just chose to model it using a Bernoulli distribution. And so, you know, P of y will be parameterized by that, right? And then how do I model P of x given y? Well, so keep changing bullets. My model for P of x given y, under the naive Bayes assumption, I assume that P of x given y is the product of these probabilities. And so I'm going to need parameters to tell me what's the probability of each word occurring, you know, if each word occurring or not occurring, conditioned on the email being spam or not spam email. Okay. Oh, because x is either 0 or 1, right? By the way I define the feature vectors, xi is either 1 or 0, depending on whether word I appears in the email, right? So by the way I define the feature vectors, xi, dxi is always 0 or 1. So by definition, if xi, you know, is either 0 or 1, then it has to be a Bernoulli distribution, right? If xi were continuous, then you might, you know, model this as Gaussian, say, and you end up like we did in Gaussian discriminative analysis. It's just that the way I constructed my features for email, xi is always binary value, and so end up with a Bernoulli here. Okay. All right. Actually, I should move on. So it turns out that this idea almost works. And here's the problem. So let's say you complete this class and you start to maybe do a class project, or and you keep working on your class project for a bit, and it becomes really good, and you want to submit your class project to a conference, right? So, you know, around, I don't know, June every year is the conference deadline for the NIPS conference. It's just the name of the conference, it's some acronym. And so maybe you know, send your project partners or send your friends email and say, hey, let's work on a project and submit to the NIPS conference. And suddenly you're getting these emails with the word NIPS in them, which you've probably never seen before. Right? And so, piece of email comes from your project partner and say, you know, about let's send a paper to the NIPS conference, and then your spam classifier will say P of x. Let's say NIPS is the 30,000th word in your dictionary, right? So x 30,000 given 1, given y equals 1, would be equal to 0. That's the maximum likelihood estimate, right? Because you've never seen the word NIPS before in your training set. So maximum likelihood of the parameter is that probability of seeing the word NIPS is 0. And similarly, you know, in, I guess, non-spam mail, the chance of seeing the word NIPS is also estimated as 0. So, when your spam classifier goes to compute P of y equals 1 given x, it will compute this, right? P of times P of y over, well, And so if you look at that term, say, this will be product from I equals 1 to 50,000 of P of xi given y. And one of those probabilities will be equal to 0 because P of x 30,000 equals 1 given y equals 1 is equal to 0. So you have a 0 in this product, and so the numerator is 0. And in the same way, it turns out the denominator will also be 0, and so you end up with, actually, all of these terms end up being 0. So you end up with P of y equals 1 given x is 0 over 0 plus 0, okay, which is undefined. And the problem with this is that it's just statistically a bad idea to say that P of x 30,000 given y is 0, right? Just because you haven't seen the word nips and you lost 2 months worth of email is sort of statistically not sound to say that therefore the chance of ever seeing this word is 0, right? And so is this idea that just because you haven't seen something before, it may mean that that event is unlikely, but it doesn't mean that it's impossible. And they're saying that if you've never seen the word nips before, then it's impossible to ever see the word nips in future emails. The chance of that is just 0. So we're going to fix this. And to motivate the fix that I'll talk about, here's the motivating example we're going to use is, let's say that you've been following the Stanford basketball team for all of their away games and been sort of tracking their wins and losses, to gather statistics and maybe, I don't know, form a betting pool about whether they're likely to win or lose the next game. Okay? So these are some of the statistics. So on, I guess, 8th of February, right, last season, they played Washington State, and they did not win. On 11th of February, they played Washington. 22nd, they played USC. Played UCLA. Played USC again. And now you want to estimate what's the chance that they'll win or lose against Louisville. All right. So, fine, the poor guys lost 5 times in a row in their away games, but it seems awfully harsh to say that, right? So it seems awfully harsh to say there's 0 chance that they'll win or lost in the 5th game. So here's the idea behind Laplace smoothing, which is that we'll estimate the probability of y being equal to 1, right? Normally, the maximum likelihood is, the maximum likelihood estimate is just the number of 1s divided by the number of 0s plus the number of 1s, okay? I hope this informal notation makes sense, right? Normally, the maximum likely estimate for sort of a win or loss for Bernoulli random variable is just the number of 1s you saw divided by the total number of examples. So it's the number of 0s you saw plus the number of 1s you saw. So in Laplace smoothing, we're going to just take each of these terms, the number of 1s, and sort of add 1 to that, number of 0s and add 1 to that, number of 1s and add 1 to that. And so in our example, instead of estimating the probability of winning the next game to be 0 divided by 5 plus 0, we'll add 1 to all of these counts. And so we say that the chance of their winning the next game is 1/7, okay? Which means that having seen them lose 5 away games in a row, we don't think it's terribly likely to win the next game, but at least we're not saying it's impossible. As a historical side note, Laplace actually came up with this method. It's called Laplace smoothing after him. When he was trying to estimate the probability that the sun will rise tomorrow, and his rationale was, in a lot of days now we've seen the sun rise, but that doesn't mean we can be absolutely certain the sun will rise tomorrow. He was using this to estimate the probability that the sun will rise tomorrow. This is kind of cool. So, and more generally, if y takes on k possible values, if you're trying to estimate the parameter of a multinomial, then you estimate p of y equals 1. Let's see, so the maximum likelihood estimate will be sum from j equals 1 to m, indicator yi equals j, divided by m, right? That's the maximum likelihood estimate of a multinomial probability of y being equal to, y equals j. Right, that's maximum likelihood estimate for the probability of y equals j. And so when you apply Laplace smoothing to that, you add 1 to the numerator and add k to the denominator if y can take up k possible values. Okay? So for naive Bayes, what that gives us is right, so that was a maximum likelihood estimate, and what you end up doing is adding 1 to the numerator and adding 2 to the denominator, and this solves the problem of the 0 probabilities. And when your friend sends you email about the NIPS conference, your spam filter will still be able to make a meaningful prediction. Okay. Shoot. Any questions about this? Yeah.
So to what extent does it make sense? Because, for instance, if you take the world of the games on the right, it's quite a reasonable assumption to say that the probability of winning is very close to 0. So I mean, the prediction should be equal to give
right.
0.
So in this case, the prediction is 1/7, right? We don't have a lot of if you see someone lose 5 games in a row, you may not have a lot of faith in them. But as an extreme example, suppose you saw them lose 1 game, right? It's just not reasonable to say that the chance of winning the next game is 0. But that's what maximum likelihood estimate will say.
Yes,
and
in such a case, it's anyway the learning algorithm doesn't have enough data.
Yeah. So the question is, given just 5 training examples, what's a reasonable estimate for the chance of winning the next game? And 1/7 is, I think, it's actually pretty reasonable. It's less than 1/5, for instance. We're saying the chance of winning the next game is less than 1/5. It turns out, under a certain set of assumptions I won't go into, under a certain set of Bayesian assumptions about the prior and posterior, this Laplace smoothing actually gives the optimal estimate, in a certain sense I won't go into, of what's the chance of winning the next game. So under a certain assumption about the Bayesian prior on the parameter. So I don't know, it actually seems like a pretty reasonable assumption to me. Although I should say, it actually turned out. No, I'm just being mean. We actually are a pretty good basketball team, but I chose a losing streak, because it's funnier that way. Let's see, shoot. Does someone want to, are there other questions about this? Okay, so there's more that I want to say about naive Bayes, but we'll do that in the next lecture. So let's wrap up for today.